Hello, I'm Rhett Davis, and I'm going to demonstrate for you now partitions in OpenAccess DM6 using a simple test application that I've written called PartSum that computes checksum operations on a large database and then allows us to compare how fast that happens both with and without partitions. So I'm going to start up here in the upper left-hand corner where I'm in the directory where I have unpacked the OpenAccess DM6 distribution. I'm assuming that it's already been compiled here, and now I'm going to take the little example code and unpack it in the examples directory, which I have actually already done. So here it is in the directory called PartSum. If we look in that directory, we'll see that we've got the partsum.cpp source file. There's also the source file for the subprocess that's going to compute for each partition. So the first thing we're going to need here is a database to run this on. I've included a simple database called testlib. Let's open up, I've got in another window down here, I've opened up Cadence Virtuoso, and so I'm going to, oops, I want that. Let's open up the library manager. So in this testlib that I'm giving you, there's a single cell called single. We'll open that up in read-only mode. And you can see it's a very small database. It's just got 16 rectangles in layer 1. And the whole point of this is just to give us something to work with. So let me lower that now. And I've also given us a very simple test application to generate these, larger databases so that we can examine this on something non-trivial. So I'm going to go ahead and run. I've got this in a separate window here because this window up here is set up to run OpenAccess DM6, and this lower window is set up to run OpenAccess OA script. And OA script currently only supports DN5, so I had to have separate environments for those. So Python genarray.py. So what this is just going to do is take a simple integer, and I'm going to give it 800. So 800 means I'm going to take this simple layout and multiply it into an 800 by 800 array, so that we can get something non-trivial. So I'm going to do that, and it just iterates through all 16 of those rectangles and copies them into this this very large array, 800 by 800. Not that large, but large enough to give us something interesting to look at. So that copy is done, and now just to sort of take a look at how big this database is, I'm going to do an ls-lh on testlib array layout. As you can see, it takes about 215 megabytes on disk, so that's about the size of the design we're working with. So that is our example design. Let me also go over here and sort of demonstrate our machine. So I'm just going to run htop in this window and leave it running. So you can see that we've got a machine with 48 logical processors and 256 gigabytes of RAM. Currently, the machine's got about 7 gigabytes used, so we got lots of free space. There's not a lot running on this machine. So all those processors are basically sitting idle. So now let me go over here and introduce the PartSum application. So I'm just going to run it without any arguments, and you can see here's basically some reminders to me about how to use it. It basically gives us what we need to create partitions and destroy them, compute this checksum operation, and also run in this multi-process mode. There's also a multi-threaded mode. I don't really have that one working yet. It's just kind of there as an example for future reference. So that is the application. I'm going to start off by creating PartSum create. I'm going to create an array of partitions, and I give it 2 integers, which are basically the sort of number. I'm going to divide it into a number of tiles, and I'm going to assign each shape to a partition in one of those tiles. So by saying 64, I'm going to create 24 total partitions in the design. Notice over here as it's running that the resident memory size is sort of climbing up. 361 megabytes, that's about how large it is. The first thing it did was it computed a checksum operation, and it got our checksum. We'll check to make sure that that's the same every time to ensure that this application is running. First thing it did was it took 13 seconds to assign each one of those shapes to a partition. That's just iterating through all the shapes and then assigning them to one of those 24 partitions, and then it saves the design, and it takes 10 seconds to save. That's one of the things that we expect with partitions, is that when you do the save operation, it looks at the partitions, and then it basically organizes all the records in the shape table so that each one of those partitions is contiguous. And that's the main way that you get speed up with partitions, is that by having a contiguous set of shapes, you can load only that portion from the disk. You don't have to load the whole database. So that is that's the basics. We saw also that it took us, how long? It said it took 9 seconds to compute the checksum, but you also see a lot more speed up when you do things repeatedly. So just checking each record once is going to kind of give us the slowest speed up. So if we want to really kick the tires on this car and see how fast is it going to run, we kind of want to run multiple times. So I'm going to run this checksum. I'm going to do that same checksum operation 10 times. So it's now computing the checksum, and as you can see, the resident size of that database went up to 426. So that's roughly the size that it's going to take if you were ever to open this database without partitions. That 215 megabytes grew to about 426. As it's going through, it's looking at every single record, and it's just summing the integers for every single x and y coordinate for each one of those rectangles, and that's how it's computing its checksum. And as you can see, it's only a single-threaded mode, so taking 100% of this processor right now. So again, it's running 10 times because we would expect that if it loads this memory one time, that successive times would be faster. And so if we computed our checksum in 9 seconds before, and we're doing it 10 times now, if there weren't any speed up from doing this, then we would expect it to take about 90 seconds to compute those checksums. But as you can see, it took 63 seconds to do this. So there's some speed up, even in single-threaded mode, from touching those records multiple times because they get loaded into memory. So that's sort of our basis of comparison now, 63. Now let's run this with partitions. So I'm going to go over here to this partsum application, and I'm going to now say multiproc. So I'm going to run it in multiprocess mode and do it 10 iterations. And when I do that, boom, you can see that it launches 24 sub-processes for each one of those partitions, and it's already done. So it ran the whole thing in 60 seconds. So, 6 seconds. So an awful lot of speed up. We'll have to do this a couple more times so that you can sort of notice it. But again, to tell you what's going on, we've got 24 partitions, and it's going to basically launch a sub-process for each one of those partitions and compute the checksum just for that partition, write it into a file, and then the parent process collects all of those checksum values and then writes that and computes the checksum again. And as you can see, it's still computing exactly the same checksum that we've got every single time. So that's how we know that this is actually working. And if you look in the code, you'll also see that it's comparing its checksum value every single time, and it prints an error if it ever sees that a different checksum value is printed. So we know that we're always getting the same checksum every single time. Let's run this again so you can just sort of notice, take notice. So first of all, you notice that those 24 processes are being launched up here. They're consuming about 100% of each one, and the resident memory was about 191 megabytes. So let's run that one more time so we can see. So the resident memory climbs up to 191 megabytes for each one of those sub-processes, and then it's done. And that time it actually took 5 seconds. So that time we got more than a factor of 10 speed up from running this operation with the partitions. So also notice that the memory size wasn't quite 1/24th. That the database was 426 megabytes when we were doing the checksum just single-threaded, but 191 when we were doing it with these partitions. So we don't get a perfect reduction by a factor of 24 in the memory of the process, but it's still quite significant. And that's the real limiting factor. That's the reason why we're getting around a factor of 10, or, I've seen up to like factor of 13 here speed up. But the reason we're not getting a factor of 24 speed up is because there's still that certain amount of memory that's needed for this process. So let's see, what else was I going to mention here? Notice also, I was going to mention that I've used 24 processes here. That's because I happen to know that that's the most speed up that I can get is with 24 sub-processes. Even though I have 48 processes here, 48 logical processors here, I'm actually using hyper-threading. So there's actually only 24 physical processes. So that's 24 caches, last level caches that are able to hold the data. So and through experimentation, I found that just on this machine, I'm not getting any more than that factor of. I'm not getting any more speed up with more or fewer processes. So that is. Let me show you one more thing here. I've created just to sort of drive this point home. If I run, I create a little application to follow the output of one of those 24 sub-processes, and it's just called follow.py. It comes with the distribution. It's very simple. All it does is it just waits for one of these output files that's being written by these sub-processes to appear, and then as soon as it appears, it does a tail-f operation on it so that you can see in real time the results of that checksum happening as they're written to disk, because the part sum application will delete all those files once they're read in. And so this will help us to run that, and it's sitting there now waiting. And if I run this part sum application again, then you can see it creates the processes, and then boom, it runs the checksum 10 times, and then we're done. So that is it. And of course, the number that you're seeing here is not the same as the checksum that we're computing up here, because it's just the checksum operation for one of those 24 partitions. So that is it. I'm going to go ahead and exit this, and we're done. And that's pretty much the demonstration. You've seen how much of a speed up we can get from these partitions. I'd encourage you to take this code and run it yourself to see what kind of speed ups you can get. One last thing that I would demonstrate here, just to make your life easier if you're trying this out, is if you want to now go and try a different size partition, so I'm going to say Python gen array, and you want to try it on something larger or smaller. I'm going to try something smaller just for kicks, and if I run this, I will, get an error. So what is my error telling me? It's telling me that I can't open the database because it's for DM6, and I only support DM5. That's, of course, because OA script currently only supports DM5, and so my script can't actually open the database. I've got the name of this design hard-coded just for simplicity and ease of testing. So it's trying to open that database, but it can't because it sees it's a DM6 database. So that's why up here in this window now, I just have to say part sum destroy. That will destroy my partitions and save them, save the database again. And now that it's saved, the database is basically like a DM5 database. I can go over here and my gen array goes a lot faster because it's creating a much smaller database this time. And now I can go up here and I can create my partitions, create 6.4, and this one goes a lot faster. I can do my checksum. I'll do it with 100 iterations to be safe. And you can see it's doing the same thing. It took 2 seconds, so it's a lot faster to. But you can see the same kinds of speed ups. If I just do 10 iterations on this one, then it'll be extremely slow because that's all I have to do in 0 seconds. So that's another reason why we want to run iterations, is because we can sort of on trivial or small databases we can examine the speed up a lot better. So that is the demonstration. As I said, good luck trying this out on your own partitions, and thanks for listening.